All right, ladies and gentlemen, welcome to Beeps and Boops. At the end of this lesson, I hope that each and every one of you will be able to, there it is, count in binary and encode characters in binary. So let's talk about binary a little bit. Actually, let's step back a little bit and talk about decimal. So in our counting system,
You're not sharing.
oh, I should share my screen. How about?
It's just our little tradition, Kyle.
Yes. One of these days. Yeah, it's like Thankful Thursdays. Somebody's got to remember it. Doesn't have to be me. All right, so let's talk about decimal. In the decimal system, our counting system, we have 10 values. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, so 10 characters that we can represent, use to represent numbers. Now, like a kind of core real math topic, and what I mean by real math is like not arithmetic, like theory of numbers kind of stuff, is that a number exists separately from your like numeral representation of it. So you could represent the exact same number in a variety of different counting systems. So like one of those is binary. Binary just has 0 and 1. We can also have more. Can anybody think of a counting system that we have used kind of extensively in this program that has more than 10 values in it?
Hexadecimal.
Hexadecimal. What's hexadecimal?
It has 16.
Yep. So hex has our 10 decimal characters, as well as A, B, C, D, E, F. That's hexadecimal. Something that's shared with all of these counting systems is the idea of places. So if I write 25,323, then we have a ones place and a tens place and a hundreds place and a thousands place and a 10,000s place. So if you want like the value that these numerals represent, you do times 10 times 100 times 1,000 times 10,000. Cool. So this exact same thing is what we do for our other counting systems too. So in hex, if I have 1, 8, A, F, then that is times 16 times 32 times 64. You just multiply them together and add them up. That's it. So with binary, we do the exact same thing. In binary, if I do 0, 1, 1, 0, all right, well, sorry, fuck. I think I did this wrong. No, I did. I did it right. Times 2 times 4 times 8. multiply them up, add them together. So this one, for example, is going to be 2, 4, 0, 0. So if I'm trying to represent this binary number in decimal, it's 6. If I'm representing that number in hexadecimal, it's also 6. Ask me some questions about this idea.
Why did they arbitrarily choose 8 for a bit? Isn't that what binary is? 8 zeros and ones?
So that has to do with computing. This is just a counting system. We can use it for all kinds of things that aren't computers. Like in general, we sort of don't, but we're getting to that. No, you can have like binary that's an arbitrary number of characters long. It doesn't have to just be 8. More questions about how binary works?
So is this kind of this sort of system how you just explained? Is this, you said this is just binary? This isn't actually how computing works. These are two separate things.
Correct. This is foundational to understanding how the computer works with binary. But right now we're just worried about this as a counting system, like decimal or hexadecimal.
You said in this example that you have up, what is this considered?
This is binary. So we'll say that
okay.
this is binary. This is decimal. And anytime you need to figure out what a binary number would be in decimal, you just do the places. Instead of tens, hundreds, thousands, it's just like times 2. 2, 4, 8, 16, 32, 64, 128. All right, cool. So now it's time for you to demonstrate your understanding of this. I want you to come up with the decimal representation of these 3 binary numbers and slack it to me. I'll give you a couple minutes. The decimal representation of these 3 binary numbers. Go.
Just to be clear, is the decimal representation that single number that will be returned, or is it like what each one will be when we multiply it?
It should be a single decimal number.
Gotcha.
Go for it. Think about what place each position represents. Multiply it up, add it together. All right, send me some of your answers if you haven't yet. And we'll work through them together. Okay, so if you didn't get these right, you are not alone. Almost nobody did. So let's work through these problems, and we're going to try this again. So for this first one, like what I did when I was just working through this just now, is you write out what all of these values are. So this place, 1 times 2 times 2 times 2 times 2. Okay, so that's what each of these places represent. So what I do when I'm working through a problem like this is I'll make this grid, and then everywhere that has a 1 has that many things. So I'll say that one's 128, this one's a 16, 2, and a 1. This one is a 32 and a 16 and an 8 and a 4. And this one is a 64 and a 16 and a 4 and a 1. So you just figure out where in the columns like those line up. And you can think of the ones as just ticks. It's like, yep, include that one. And then you add them together. So all right, for this first one, 128 plus 16 plus 2 plus 1, 147. This next one, $32 plus 16 plus 8 plus 4 is 60. This one is 64 plus 16 plus 4 plus 1, 85. Again, if you didn't get that right, almost none of you did. So hopefully this is a little bit clearer now. Ask me some questions, let me help.
So as the numbers get longer, like the combinations, the value or what you multiply it by just keeps on doubling?
Correct. If we had 9 characters in there, that biggest place would be 256. And then 1024. It grows the same direction that decimal numbers do. Sometimes to like clarify what direction we're talking about, we'll call this the most significant bit and the least significant bit. More questions about how this counting process works?
So like in B and C, you don't need the zeros at the very left-hand side.
Yeah, exactly. You could leave them out. As we're going to see when we talk about the bytes and the next part, there are very good reasons to have like a set number of things, even if you're not using the left side. But yeah, they don't do anything, just like decimal. Other questions about counting in binary? Cool. Let's do a couple more. This one will be so let me line these up a little bit better. Okay, same thing. Translate these from binary to decimal. Couple minutes. Go. All right, fire them off. All right, much stronger this time. So if we do this again and say that this is 1, 2, 4, 8, 16, 32, 64, 128. Then we can look at each of these columns and see whether or not it includes that. So that's 8 and 4 and 2 and 1. So that's 3 and 7 and 15. So if we represent that number with decimal, it's 15. This one is 128, 64, 32, and 16. And when you add those together, you get 240. This one is 64 and 32 and 4 and 2 and 1. And if we add those together, we get 103. That is how we count in binary. Like a big mind blower abstract takeaway from this whole thing should be that a number and the numerals that you use to represent that number are not the same thing. We can represent the same concept of a number with a lot of different counting systems. Questions about binary? Cool. So, I won't let me scroll anymore. Objective accomplished. So, our second objective is encoding characters in binary. All right, so you can count using a different counting system. Who gives a shit? We give a shit. Why do you think we use binary with computers? Why not decimal? Why not hex? Why not anything else? Why did we pick binary?
Because you can represent a number with an on and off electrical signal.
Yeah, that's exactly why. So like, it's funny, if any of you were in the happy hour room with that engineer from IBM at the last happy hour, like he described it very well. Originally, what they wanted to do was if you send some electrical signal to something, you would measure the voltage and turn that into a number. And so if that is 7 volts, you'd say, all right, well, that signal represented 7. Can anybody think of the problem with that? And a bigger one, 31.4.
If you want to measure a really large number, that's a whole lot of voltage.
That is true. That's not why, though. Good guess. Because we could just do 1 through 10. 1 volt, 2 volt, 3 volt, 4 volt, up to 9 volt. And then just start over again. What was the problem with trying to detect the voltage?
It fluctuates.
It fluctuates. It's very difficult to keep something a precise, consistent voltage. So instead, what they did is if the voltage is over 5, 1, else 0. Easy. That's enough wiggle room that like you're not going to accidentally get 5 volts. It might be 5.1, it might be 7.9, but if there's at least 5 volts there, we're going to call that a 1. All right, so now we can use the binary counting system with electronics. That's pretty cool. But we need a way to delineate. All right, when is it another number you're sending me? And when are we just making the current thing that we're doing bigger? So that's where bytes come from. Well, actually, hang on, let me rephrase that. So I can send, like, think of it kind of like almost Morse code, where I go 5 volts, 5 volts, less than 5 volts, less than 5 volts, 5 volts, less than 5, less than 5, 5 volts. So that's 1, 1, 0, 0, 1, 0, 0, 1. So over like a period of time, we go bzz, 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 and it's able to read whatever the decimal representation of that is. So that's 128, 64, 1, 2, 4, 8. So 132, 182, 183. So if I send that sequence of beeps and boops over, your computer goes 183. Neat. Now with 183, there's not a whole lot we can do with just that, right? And so we need to send more than one number over if we're going to get any work done. But how does it know that the next set of beeps and boops is a different character and not just the 256th place of this same number I did? Well, it turns out we call each of these a bit. And if we group those bits into 8s, we can call them bytes. So that's a bit. This whole thing is a byte. And I can even say like, all right, each of these characters takes up 2 bytes. Each of these characters takes up 1 byte. By the way, the next like set of shit I'm gonna send you, each of them are 4 bytes long. You can like make an agreement with the thing that you're sending about how big each of these numbers are gonna be. And then it knows where to delineate. I imagine the question you're asking yourself right now is like, okay, you send me a sequence of numbers. What the fuck do I do with that? We're getting there. Questions about bits and bytes.
Bits, or are they more?
I'm sorry, say that again?
Are bytes generally 8 bits, or are they more?
That is the
Okay.
definition of a byte, is 8 bits.
8 bits, okay.
You could have numbers that are bigger than that. Those would be multiple bytes.
So then what we've actually been doing is kind of evaluating the bytes then, like the 183 and all those other ones?
Yeah, so that's this encoding piece that we're gonna wrap up with. But other questions about bits and bytes?
So something talking about storage, if it's 1 megabyte, it can just store 1024 bytes.
Correct.
So it's just that's how many strings of numbers it can store. Okay.
Yep. That's exactly it. Cool. So let's talk about what it does with these numbers we give it. Go ahead and pull up in your browser ASCII, ASCII, and look up ASCII table. So on the left column of this is the decimal representation of a number between 1 and 255, which coincidentally is how many numbers we can represent with 1 byte. And look, we've got these characters, we've got the decimal numbers, we've got some punctuation, we've got lowercase alpha characters, we've got uppercase alpha characters, we have the alpha symbol or the @ symbol, a couple of other ones. Pretty much all the stuff that's on your keyboard. We also have like a couple what are called diacritical marks, extensions of the Latin alphabet, a couple of Greek characters. Who can follow how these two things connect?
This is an unrelated, maybe dumb question, but is there no overlap in what bit or with what bytes evaluate to? Is it like can you have 2 bytes that evaluate to the same, or how do I say this? Can you have 2 bytes that evaluate to the same number that are different?
Nope. It is a like thorough counting system. With 1 byte, you can count the numbers between 0 and 255, and that's it. It's not immediately obvious just looking at it, but there's no duplicates with those things. You can represent every integer with it only once with 8 binary numbers. Or 8
Some
binary
math magic.
I know, it's fucking bonkers. If you think about it a while, like get really high tonight and think about it for a while, it makes a lot of sense. But that was not a thing that was immediately obvious to me either.
So the computer is just evaluating the byte to its decimal equivalency and then converting it into an ASCII character.
That's like a very human way to think of it, but yes.
Mm-hmm.
Remember, the computer is just a rock we tricked into thinking. Like it never gets quite that high level, but yes, that is like effectively what that process is. And so it goes 183. Oh, I know 183. 183 is this thing. And it goes, okay, cool, what's the next byte? And so maybe I send it 75, that's a capital K. Then maybe I send it 121, well, that's a Y. 108, L. 101, E. And so I've sent it Kyle.
And it's also got it in like hex and then like what's octadecimal?
Yes, or no, it's eight places, octal.
Ah.
So hex is 16, oct is 8. One of the reasons that we like counting in 8s and 16s and stuff in computers is because of the bytes.
What is the purpose of 176 to 178? Just like these like dotted field patterns.
Those are for, shoot, let me see if I can make one show up. Oh, by the way, like, yeah, I just made a web request to Google. Check it out. That's the Google homepage. Fuck, that went too quickly though. Shit. Well, like this has a progress bar on it, and it uses those to indicate progress in the command line. Same thing with these. They like draw boxes around like documentation and stuff. Other questions about how this works?
Have the character equivalents like changed over time to reflect what most people need?
Kind of. So you might be like asking yourself, 256 characters, I see more than that on my screen. Like, and what if it's Chinese characters, Arabic characters? It seems like we would need more than like just 255 things. How right you are. Enter UTF-8. You know that thing that you're always putting as your character encoding in your HTML documents? So it turns out the first 255 places in this are the exact same as ASCII. Then we got these characters and a couple others. All right, cool. Except we also have lots more. So total number of characters. That's a lot of characters that you can represent with Unicode. Any guesses what the 8 means in UTF-8?
Yes, an 8-bit.
Close.
Like the 8th version of it?
Nope. Also good guess.
8 different languages?
Nope. 8 bytes per character. Every single character in UTF-8 is represented by 8 bytes. So it's looking for 8 of these to come through to identify every single character. How much is 8 bytes? How big a number can you represent with that? Well, 2,164,864. I think you can actually represent significantly more than that with 8 bytes, but that's how many characters have like already been mapped to it.
So if that's 8 bytes, then like, so does that explain like why, like as computing got more powerful, why graphics got better? Because suddenly we can like represent all these additional colors and symbols and stuff that we couldn't get before?
That's a related idea. This is why like we have emojis and stuff that you can copy and paste and send to people, even though those are like basically graphics. But yeah, with 200 million characters, we can represent the entire Chinese alphabet. We can represent all of Arabic. We can represent an growing number of emoji. We got a lot of characters we can do with 8 bytes.
So the ASCII characters include like the plus addition sign.
Mhm.
So at this point, can the computer now do math just knowing the character?
Sort of. Keep in mind that like the way that your computer is doing the math is with like logic gates and stuff. It's working at a pretty low level to actually perform that math, but now you can give it an instruction in like a way more human readable way that can make it do that. And specifically what that looks like, it's kind of like programming, except way down. It's a thing called machine code. Things like this: call, move, and subtract. They're really like short and abbreviated because we don't want to use 8 bytes to represent an instruction. That means that like a program's super slow. So we have these like really tight hex representations that boil down to these instructions. So if you were going to write them into your computer to program a CPU, for example, you would be writing like this.
Is this kind of stuff in like sort of like a prerequisite imperative to know if you're going to write your own programming language?
Yes. Well, actually, like that's not all that fair either. This stuff is imperative to know if you're writing your own low-level programming language. If you were going to make like a replacement for JavaScript or something, JavaScript compiles down to C++. C++ is compiling down to assembly. Assembly is compiling down to machine code. Machine code is compiling down to binary. There's a lot of layers of like compilation happening there. You need to know the one below you, but it's not absolutely imperative that you know much further than that. Okay, one more thing I want to leave you with. So, question about, all right, well, is this why graphics got better? Because we can do so many more colors with this? Kinda. What that really had to do with was the jump from 32-bit to 64-bit. Other than like being in binary, it doesn't have anything to do with the encoding thing that we just talked about. Imagine like your RAM in your computer as just a bunch of little boxes. And in each of those boxes, you can store a byte. You can store 2 bytes. You can store whatever. Okay, so with 32-bit, let's see how big a number we can represent with 32-bit. Biggest number in 32-bit. All right, so hundreds, thousands, millions, 2 billion, 2.1 billion. of these little boxes we can represent with that. Think of those like phone numbers or like postal addresses or something like that. That's how many different places in memory we can describe. Hey, what mailbox do you want me to put that in? Oh, how about number 1,256,005? So when you're saying in a low-level programming language, where do I want to save that? We'll save it over there. But we're limited by how many of those addresses we have. Ends up actually not being that many. In fact, that's about 4 gigabytes, which in the 32-bit computing era was the maximum amount of RAM that we could use. That was the maximum number of addresses in that RAM that we could describe. A lot of people made the mistake when 64-bit happened of assuming that we doubled the total amount of space. 32 to 64-bit isn't doubling. If we go back to our binary counting stuff, what would it mean to double the total amount of space that we have here? So this is 256. If I want to be able to describe 512 things, how many more bits do I need?
Two more.
Oop, one more. Because with one, I get 256 plus all of these things that I already had before.
Yeah, because it's doubled. It's like it's 128 plus what 256. So that's
Yeah. Plus 64 plus 32 plus 16 equals 512. So going from 32-bit to 33-bit would be doubling. And then we double again and again and again and again. So how many memory addresses do we have with 64-bit? A whole fucking lot. How much RAM with 64-bit? Nope. Nope. How much memory with 64-bit? 16 exabytes of RAM. That's a lot. That's a shit ton. That's why we can do so much more detailed stuff, bigger programs, more aggressive calculations, all that kind of stuff. And then like NES was 8-bit. That puts a limit on how much memory you can interact with in the program, how many colors you can have, all that sort of stuff. Cool, there's your intro to beeps and boops. Questions?
It's the 64-bit. That's not referencing the amount of RAM your computer can have. That's the amount of information your processor can access at any one time, or?
No, that is how much RAM you can have.
Okay.
That's how many memory addresses your operating system, your CPU, I guess, is allowed to, or is able to deal with.
So if you're gonna take like if you're gonna take 4 bytes and convert it to 32-bit, are you gonna keep following? You're gonna keep following that same rubric of like 1, then 2, then 4, then 8, then
Correct.
16.
Yep. Yeah, just
Gotcha.
keep going. So we talked about how we count in binary. It's like tens place, hundreds place, thousands place, just with doubling things. We talked about how, all right, cool. If we think of those numbers as decimals, with 1 byte, we get 255 options. We can then map the ASCII characters to those numbers. So like now we can store characters effectively. And if we take that same concept and just make it bigger, well, with 8 bytes, we can store all kinds of characters. 2.1 million of them, in fact. And if we take this same concept of like big ass binary numbers, we can also say exactly where in a computer something should be stored. Pretty dope.
Do you think there's ever going to be a situation where they have to increase it to 128-bit? Like, that's just so much.
Well, like not in consumer computing ever. Really, what we'd be looking at is shifting the model entirely. That's what quantum computing is all about. Quantum computing is this original idea with like 7.1 volts is 7.1. Because it's 2020 and not like 1930 or whatever when they were trying to do this stuff. We can absolutely have things have consistent voltages now.
So would those voltages go into decimal ranges then? So you can have like the full range of, I guess voltage, there's not necessarily like an upper limit to it, right? So.
Right. And so like the real answer to your question is I have no fucking idea. That is way like, I mean, I'm an application developer. I'm not even supposed to know this shit.
We're not doing quantum computing in this program? What's going on?
I make apps, man. But like all the stuff we just talked about was your first year of computer science school. No shit. You probably wouldn't have like picked up much more than this in a first year of a CS program.
So that kind of ties into my questions, like, so when would we really use this information, or what, like, why do we need to know this stuff? Or, I mean, I know for size, but just like, what's the application of this?
Because I had a Code Wars problem, Shelly, and I asked Kyle about it.
I mean, it's fascinating, but I'm just like, you know.
Well, interviews.
Okay.
People ask you this shit in interviews. And also like, it can be helpful to know, especially like the character encoding thing. Like, I don't know, that's helped me debug something or troubleshoot it faster than I would have otherwise, just knowing that that's what was happening under the hood. Because sometimes you can see something that's like, I think the character encoding on this got borked somehow. But like, no, outside of that, there is not a ton of usefulness to this kind of thing in application development. There totally is an IoT. Like if you do work with Raspberry Pis and stuff, hey, guess how you like interact with your sensors and stuff? They send you 5 volts on one of those fucking pins, and you can detect whether or not they sent you 5 volts, and then you can do things with that. But for making like e-commerce sites and stuff, no, this like never comes up. Anything else? Thank you. Hope this is helpful.
This is a super fun lesson.
Yeah. Thanks, Kyle.
If you want a way to test whether or not you can encode characters in binary, see what binary your name would have to be. See if you can do that translation. You can send it to me to double check if you want, but elsewise, survey's coming out now.
Thank you.
Yep.